Hello friends, last week we simulated pendulum and mass spring damper system in MATLAB and Simulink using different methodologies such as state space, transfer function and nonlinear methods. This week we will be simulating aircraft 6 degree of freedom equations of motion in MATLAB and Simulink. Before we step onto that, it's good starting point to simulate first 3 degree of freedom equations of motion. Now let us go back to MATLAB. So this is how it is looks like 3 degree of freedom block. So this is 3 of block in body axis, and these are the equations of motion axb, azb, axc, aze, and so on so forth. What we will do is we'll do the derivation of these equations directly from 6th equations, and then we'll simulate in MATLAB and then in Simulink, and then we'll use the 3 of block. Now let us go back to the 6th equations of motion. Let me rewrite the equations starting with the translational dynamics. We have u dot equals to 1 upon m fx a plus fx p plus fx g minus qw plus rv. Here A represents aerodynamic forces, P is propulsive forces, and G is the gravitational forces. Similarly, we have V dot equals to 1 upon m Fy aerodynamic forces plus Fy propulsive forces plus Fy gravitational forces minus R into U plus P into W. W dot we have 1 upon m Fz aerodynamic forces, propulsive forces and gravitational forces minus Pv plus Q into U. Let me denote this as equation number 15. I am continuing the numbering from the previous lectures, and where the gravitational forces Fxg, we know that it is minus mg sin theta, Fy gravitational forces is given as mg sin phi cos theta, and Fz gravitational forces is mg cos phi cos theta. So again, I will not be going into detail how this equation has arrived, since that is not the intent of this course. Next is the rotational dynamics. So we have 12 states, so there will be 12 equations. Rolling moment L equals to P dot Ix minus R dot Ixz plus QR Iz minus Iy minus Ixz to P into Q. My, I am writing pitching moment about y axis. I am not writing y just to make it different from the mass so that you do not get confused. Q dot Iy plus R into P Ix minus Iz plus Ixz P square minus R square. Finally, yawing moment equation minus Ixz into P dot plus Iz into R dot plus P into Q Iy minus Ix plus Ix Z Q into R. Let me take this as equation number 16. Then we have rotational kinematics. Phi dot equals to P plus Q sin phi tan theta plus R cos phi tan theta. Theta dot equals to Q cos phi minus R sin phi, and xi dot is Q secant theta sin phi plus R secant theta cos phi. Let me take this as equation number 17. Finally, we are left with translational kinematics. So that is written as xe ye dot ze dot, I am writing in a matrix form. We have cos xi cos theta sin xi cos theta minus sin theta. Here we have cos xi sin theta sin phi minus sin xi cos phi, sin xi sin theta sin phi plus cos xi cos phi cos theta sin phi. Here we have cos xi sin theta cos phi plus sin xi sin phi sin xi sin theta cos phi minus cos xi and sin phi, and here cos theta and cos phi. This is u, v and w. So let me take this as equation number 18. Now Freedhoff-Bloch considers the motion in longitudinal xz plane. Here we have side velocity v equals to rates, p equals to r equals to bank angle phi equals to xi, and side force is 0. Hence it greatly simplifies these equations, and finally we can write the equations in this format: u dot equals to 1 upon m fx a plus fx p minus mg sin theta minus q into w. W dot equals to 1 upon m fz a plus fz p plus mg cos theta plus q into u. Then we have q dot equals to my upon iy. All other terms are cancelled. So theta dot equals to q, and xe dot equals to u cos theta plus w sin theta, ze dot equals to minus u sin theta plus w cos theta. So these are the reduced equations of motion in the longitudinal plane. So that is, we have the motion in the forward direction, that is u in the body x axis, and then the motion is in w, that is downward direction, and finally we have pitching moment about y axis. So here we need to model these forces and moments that we are seeing over here. We need to model these forces and as well as moments. We assume that thrust forces are acting through aircraft CG in body x axis. So we can represent propulsive forces as Fxp equals to thrust maximum thrust into delta T, where T max is the maximum engine thrust and delta T varies from 0 to 1. So 1 means we have maximum throttle, and if delta T is 0, that means there is no engine thrust, that is 0. And we assume that propulsive forces in z direction is 0. Now aerodynamic forces are lift and the drag, which acts in the stability frame where x axis is aligned with the velocity vector. So let me model these forces. So we need to transform these forces to the body frame. So aerodynamic forces are acting in the stability frame where x axis is aligned with the velocity vector. This is the attack angle, this is the body x axis, this is ZB, and the lift vector will be perpendicular to the velocity vector. This is the lift, and drag will be the parallel with the velocity but in opposite direction. This is drag. If this is the attack angle alpha, then this will also be alpha, and this angle will also be alpha. So what we'll do is we'll transform these lift forces to the body x axis. Beginning with the lift force, we have here it will be L cos alpha, and here it will be L sin alpha. Similarly, resolving the forces drag, here it will be d cos alpha, here we have d sin alpha. So finally we can write forces in x direction, aerodynamic forces to be specific, we have L sin alpha minus d cos alpha. So this direction is actually positive, and similarly drag is acting in opposite direction, so this is negative, this direction is negative, this is positive. Similarly we write Fz A equals to ZB, we have minus L cos alpha minus d sin alpha. Now how do we get this lift and drag? We know that lift is given by this expression L equals to half rho v square SCL, where rho is the density, v is the total velocity, s is the wing area, CL is the lift coefficient, and drag is given as half rho v square s into CD. Now we need to model this CL and CD. CL is given as CL naught plus CL alpha into alpha plus CL delta E into delta E. I hope you are aware of these terms CL naught, CL alpha and CL delta E. Here we are omitting Q dependencies. For simplicity, you can add as per your wish. Similarly, we have CD equals to CD naught plus CD alpha or you can also model CD equals to CD naught plus kcl square if that is given. Now what we are left is pitching moment about y axis, body y axis. So that means pitching moment, we know it is written as half rho v square s into c into cm. Cm is the pitching moment, c is the chord, and the modeling of Cm can be done in this way. Cm equals to Cm naught plus Cm alpha into alpha plus Cm delta E into delta E. Fine. Now finally we can write u dot w dot q dot can be written as u dot equals to 1 upon m L sin alpha minus d cos alpha plus T max to delta T minus g sin theta minus q w. So let me take this term as AXE. I am just aligning the nomenclature with what is given in the 3 of block. What is AXE? AXE is acceleration of body with respect to inertial reference frame. So AXE equals 1 by m L sin alpha minus d cos alpha plus T max into delta T minus g sin theta. Further, let me write this as AXE equals to, what is this term? This is forces in x direction, forces in x direction, which is nothing but aerodynamic or propulsive forces divided by m minus g sin theta. Now similarly we can write w dot is given as 1 upon m minus L cos alpha minus d sin alpha plus g cos theta plus q into u. Similarly take this as a z e. So w dot is written as a z e plus q into u, where a z e is 1 upon m minus L cos alpha minus d sin alpha plus g cos theta. Now here AZE further can be written as forces in z direction, body z direction. So these are nothing but aerodynamic and propulsive forces divided by m plus g cos theta. And further, if you want to write fza comma p is minus L cos alpha minus d sin alpha. I am writing in this format because we will be using this in our simulation. Now finally, writing 3 degree of freedom equations as AXB, that is nothing but u dot equals AXE minus Q into W, AZB equals to W dot equals to AZE plus Q into U. Then we have theta dot equals to Q, Q dot equals to My upon Iy, X dot E equals U cos theta plus W sin theta, Z dot E equals to minus U sin theta plus W cos theta. Now let me take these equations as equation number 19. All right. So where AXB and AZB are the accelerations of body with respect to body fixed coordinate frame. Now let us check these equations directly in the MATLAB 3DOF block. So here we have AXB u dot equals to AXE minus QW, u dot equals to AXE minus QW, W dot is AZE plus Q into U, AZE plus Q into U, then theta dot equals to Q, then theta dot equals to Q, Q dot is My upon Iy, then X dot E equals to U cos theta plus W sin theta, U cos theta plus W sin theta, and Z dot E is minus U sin theta minus U sin theta plus W cos theta. All right. Now, before I proceed further, I have seen students struggle with the units of these equations, whether they have to use in the numericals or in Simulink. So I always suggest to match the units on the left hand sides and the right hand side. So for example, AXB or U dot, here U dot, this is the in meters per second square. So U dot unit should be meters per second square. So in U dot, what do we have? We have AXE minus Q into W. So here Q is the rate, that is radians per second, and W is what? That is the velocity, meters per second. So we get radians meters per second square, and we know the radian is some angle upon angle which is unitless. So finally we have meters per second square. So this QW is meters per second square. So you have to ensure that Q is not in the degrees per second, it should be in radians per second only. All right. And MATLAB by default, it takes the values in radians. So we have to be absolutely sure what unit we are using. Now coming to AXE. Now what is AXE? AXE was Fx, aerodynamic and propulsive forces, divided by m minus g sine theta. So here g unit is meters per second square. Here theta is in radians. So we get meters per second square, which is all right. Now if we consider force in newtons and the mass is in kgs, this can be further simplified as kilogram meters per second square divided by kilogram. So finally we have meters per second square. So ensure this force is always in newtons. So Fx of A comma P, we know it is written as L sine alpha minus D cos alpha plus T max into delta T. Delta T is unitless, it is 0 to 1, and if T max is given in kgs, convert it to newtons. So, we have this in newtons. Similarly, this angle should be in radians and this drag should be in newtons. This L should be in newtons. Now, what is L? L is the lift, which is given as L equals to half rho V square S into CL. So, this L unit should be in newtons. So, density is given as kilogram per meter cube. Then we have velocity meters per second or meter square per second square, and area is in meter square. So, we have kilogram, this is meter power 4, this is meter cube. So, we have kilogram meters per second square, which is nothing but newtons. All right. So, lift should be, force should be in newtons. Then we have theta dot equals to q. So, this is radians per second, it should be radians per second, and this is rate, it is already radians per second. It should not be in degrees per second. All right. Then we have movement about y axis equals to half rho v square s cm. So, this next one variable was q dot. Q dot is my upon iy. All right. So, q unit is radians per second. This is q dot. It should be radians per second square, or it should be simply 1 upon second square. Now, let us see what is the unit of my in this case. Movement about y axis, half rho v square sc into cm. Again, density is in kilogram per meter cube. Velocity is meters per second. So, we have meter square per second square. Area is in meters square. Cm does not have any unit. C is chord, which is given in meters. So, we have kilogram meter square per second square. What about moment of inertia? The unit of moment of inertia is kilogram meter square. So, finally, we have my upon iy. My we got kilogram meter square per second square, and iy is kilogram meter square. This goes, finally we have 1 upon second square. So, we have 1 upon second square, and this is q dot is 1 upon second square. All right. Now, the final one on the left is x dot e. X dot e is given as u cos theta plus w sin theta. So, this unit should be meters per second, so velocity. So, this angle will be in radians, angle is in radians, and this is again the unit of meters per second. All right. So, similarly, you can find it for ze dot, unit also will be in meters per second. So, now I hope there is no confusion in the units. Now, further we need some aircraft data for this simulation. So, let us stop it here. We will begin with the aircraft data and the simulation in the next lecture. Thank you.